In an increasingly innovative environment, traditional architectural and urban design methods cannot facilitate the complexity of the evolving context. High-density and low-coverage architecture allows for high-quality inhabitation with less land use and carbon footprint, therefore giving back more land for the wilderness, wildlife and supporting planetary health. In modern-day environments, architecture meets a demand for high density by sacrificing high quality of both living conditions and sustainability. It is becoming critical to consider future lifestyles for a younger population that reflect growing social patterns and community formations through co-living and co-working, in close proximity to nature. In response to the speculative evolving context, the introduced system will establish both higher density and higher quality living conditions. A system that is able to demonstrate flexibility and adaptability. Early explorations consisted of experimental agent systems that demonstrate adaptability to the physical landscape. Voxelized agent systems were integrated with modular components to create complex building systems. Through extensive explorations of the agent system, patterns and agent systems that displayed directionality most effectively and efficiently highlighted the textures of the landscape. Its potential to sustain display of adaptability at various scales suggested the project focus. Directionality in different scales refer to agent systems, voxelization, component design, and aggregation. Agent systems on a larger macro field condition showed spatial porosity, suggesting potential for green pockets that are able to provide a better living environment in between built systems. The aim for porosity is not just based upon integrating green spaces within the architectural form, but the ability to give back space for the wilderness from the built environment. Further experimentation on directionality and connectivity were conducted through voxelizations on large characterized chunks. Numerous chunks were clustered together to demonstrate a densely built environment, others displayed looseness, and a few were able to accentuate the profile of the landscape ridges to create terrace-like conditions. The presence of spatial porosity within architectural compositions was essential in order to address high-quality living conditions and adaptability to the physical context. To prevent a plain blanket or cluster of form that just merely covered the landscape, a focus of directionality and a vertical orientation will further articulate the radial asymmetry found in the larger scale of our agents, voxelization and field conditions. Along with emphasizing the connectivity and the alignment of components, creating patterns and textures on the aggregated forms. A combination of directionality within the field and the design of components create a mid-scale directional texture and patternation. Further iterative analysis resulted in a visualization of a moving force within the overall architectural system, displaying a recognizable quality. It allowed for the ability to control the window opening towards a certain orientation. However, in the early stages of development, a dominant single direction consistent through the whole system forced a limitation of flexibility for light exposure and view conditions. Thus, a new system was introduced, a rule-based system that allowed improved efficiency of component connections, resulting in both improved flexibility but also sensitivity to existing landscape. The concept of directionality establishes the relationship between the wide-scale direction of the components and the individualized orientation defined by light exposure and view conditions. This creates an enhanced system that facilitates higher quality living conditions. Some early iterations, chunks and towers tested the ability of the local control on the window's opening of every single component. Then later testing on the global control of the window's opening system and component orientation of the large aggregation. Directionality of the current system, directionality in conjunction with the light is then further developing the system. The relationship between the direction of the architectural components and the orientation of the components towards the light within the system was established. The idea of directionality was informing the process of developing the system and design decision-making. To further explain and showcase our latest stage of the system, a pilot site was chosen for testing. The chosen site is Petrinja, a town in central Croatia. Addressing Petrinja's declining economy after being devastated by the earthquake, the system will be able to provide the solution of re-inhabitation, by introducing new lifestyles reflecting co-living, co-working, and high-quality living conditions. Once a building area was located, agent system was introduced to the site. Agent iterations were made to show different densities of cluster building systems. The first one has an adequate green pocket and opening for the wilderness. The second one's porous areas acting as green pockets were not large enough for the aggregation. The third one was clustering and blanketing the landscape with a new system. Scenario 1, Medium Density. A small chunk was picked to explain the system we developed. Then agent field and voxel field were then used as a reference to apply the rule-based system for creating the co-living, co-working living system. Sustainable building material cross-laminated timber was applied from early design of components. They offer significant structural simplicity, strength and energy efficiency. Simple inputs, one universal component that is able to switch to different types by creating distinct additional windows on different sides. This allows the space to change from private use to communal shared space as well as provide adaptable lighting conditions within the architectural modules. By applying algorithmic rule system for how components connect to each other, they are able to create different configurations, to have a different set of combinatorics to create different or rich spatial quality within the aggregation, testing out different combinations with double modules which can potentially form one housing apartment. Some configurations expand a space vertically. Some create a wider space. Some join top and bottom to create horizontal connection and double height spaces. Control of orientation of components was applied in aggregation scale. A small chunk was picked from the medium density showcasing the smart system. This system allows the aggregation to integrate multi-directionality, which creates a more interactive response to the site. There is control on the orientation of each architectural form towards the sun and gain maximum views and natural light in the system. This can potentially create more diverse internal and external spatial combinations and unique views and light conditions between each module. This provides a more intelligent way of building the housing system. Different orientations were shown here. The ones able to follow the overall growth trend of the aggregation was picked. It also explores the long side of the component to capture the view and light for the next feature of the system, which is the additional system. Based on the sun data analysis, additional windows were added where they were highlighted in orange and yellow in the solar analysis. It is to open up the additional windows on the two sides of the component, so they can get more views from the hill on the left side of the aggregation and the riverside as well as natural light. It also creates some subtle patternation with the windows facing in different ways. Light analysis showing how the light gets in within the architectural space during a day. This complex structure and opening allow natural light to get within the system, the area where most explode with the light. Additional balconies were applied in the same technique of using data for maximum sunlight. The roofed-up space was activated for creating some balcony area and shared space for inhabitants to enjoy this vertical landscape. By going inside the system can explain how the system works internally, showing all of the connectivity of the internal circulation on each level. 3 cores were located and highlighted in yellow, and all components' connectivity were shown at all levels. Plans were shown here to explain the internal space of the aggregation and how the shared space is divided with the private apartment area within a chunk. The private housing areas were highlighted in blue and shared areas were highlighted in orange. Balcony areas were highlighted in yellow. Each module area is 40 square meters. Shared spaces are 39%. Residential living are 45%. Semi-open shared balconies are 16%. Shared spaces were located in between the housing area, so that allows all inhabitants in housing to have access to the shared area. Balcony areas create semi-open shared areas as well as the lookout space for inhabitants, which allow them to connect to the community and build up the connection with surrounding nature. By zooming in, different configurations emerge in this small chunk. There is a studio type of housing that only has 40 square meters, and also has an apartment type that can be up to 120 square meters, allowing more people to live together, which can attract and bring different needs and groups of people to inhabit in the system. Also, 2 types of shared space were created. One is full glazed with glass, another one is semi-open, allowing cross-ventilation and building up a connection with surrounding nature. The housing and shared area blended together to create this co-living co-working enrichment connected to nature. The system creates a void opening inside the building form which allows natural light to get inside and cross-ventilation. Some connection with the same modulus in different orientations, increasing the volume of the spaces and creating unique and different cluster spatial qualities in different levels. Fully glazed space can be shared and gathering space, but also can be area for co-working. Balcony spaces are semi-open shared spaces. And housing apartments are on either side of the shared space. Simple input, complex output. Even when working with just one simple module, when they come together, they create different sets of combinatorics and poly-resolution spatial conditions. This provides more diverse and rich spatial experiences for the inhabitants. Some views are shown here to give a new perspective of the exterior. The exterior aesthetic qualities of each elevation are distinct from each other. It gives different tectonic quality when viewing the architectural form from various angles. Communal space and housing. Semi-opening communal space in between the housing components. Housing type has the view of nature on the outside. Highlighting again that only one universal component is being used to aggregate, and this created a rich, poly-resolution tectonic behavior. Scenario 2 is introduced where the capacity of the system is tested for super high density. There are 8,052 architectural components. Extreme density can provide communal space of 187,160 square meters, housing of 215,954 square meters, balcony of 76,783 square meters. If all housing type is studio, it will be around 5,398 components of 40 square meter apartments. The system is able to adapt and build in different sites. This is a system that could be applied in various conditions beyond just the featured pilot test site in Petrinia. For instance, we can test very high density configurations with it for a more populated context. If pushed to extreme, even places such as Mumbai that is known for ultra high density and slum conditions. nDirection system is flexible enough to adapt to many situations. It's able to provide a co-living, co-working, high-quality living environment, from small town development to towering skyscrapers. And yet nDirection system has the potential to keep refining and evolving to meet demand for the future patterns of living.